So to understand what's really going on here, it helps to look at the compiler-generated code. So I have up here on my screen, we've gone to a website called sharplab.io. If you've never heard of SharpLab, this is a really, really cool website where you can see what the compiler is actually doing with your code. In fact, it's so good that the .NET team at Microsoft actually uses this, because we can see here that it has all the different branches of the Roslyn repo, different platforms. So literally, the C# team, when they're implementing new features for us, they'll come in here to try them out. So highly recommend sharplab.io if you haven't used it before. But what we have here on the left is that same code. So this is our get libraries method. And on the right, this is what the compiler has generated. So if you don't know, the way the compiler works, when you first click compile, it does what's called lowering. So it takes the code we write and turns it back into something that the compiler can understand. Because if you think about it, the compiler's got to support all the way back to C#1, and when C#1 was invented, async await didn't exist. Like heck, multi-threading, thread pools wasn't even really a thing. Even things like we get like var, that gets lowered back into the type so that it can go through the compiler in a way it understands. And what happens here with our async task method is we see that the compiler has created a private struct that inherits from iasync state machine. Now, quick fun fact, we're looking at the code as if it was in compiled for release mode. When you're in debug mode, it looks a little different. It'll be a class, but when we're compiling for release, the compiler goes ahead and optimizes a little bit for us. So we get a private struct, and right away that's a little weird, right? Because I just wrote a method, but now the compiler-generated code is this struct that inherits from iasync state machine. It's got all these funny names in it, like angle bracket, get libraries, d__2, and this, if you squint and look closely, this is the name of my method. This is my get libraries method, but what the compiler does, because it's generating this class and it doesn't want to have a naming conflict with any other classes or structs that already exist in our class, it adds these angle brackets, which is a cool way to cheat because we can't do that. Like we can't add an angle bracket in our code. We'll get all sorts of weird errors for our class names. And the compiler knows that, so it writes some illegal code that it knows we'll never be able to write. That way we don't have any overlap with its compiler-generated code. But let's take a look at what's going on here. So inside this method, or inside this struct, is a method called moveNext. And right away, this is something that perplexed me when I first started using async await. I've been making iOS and Android apps in C# using Xamarin and .NET MAUI for about 8 years now. And I'll never forget when I first published my app to the App Store, I kept seeing these weird stack traces. I'd get back these crash reports and bug reports from the app, and moveNext would be everywhere. And I was like, what is this? Because I never wrote a method called moveNext. Turns out the whole time it was just the compiler generating it for me. But what moveNext is essentially a giant state machine, or more explicitly, or more specifically, it's a giant switch statement. And inside of this switch statement, the compiler adds a case every time we use the await keyword. So in this example, we're using the await keyword 3 times, and you can see that the compiler generated case 0, case 1, and case 2 for us. And there's also this default case here, which every time this gets generated, it'll always have at least the default case, and then every time we add the await keyword in our method, the compiler adds another case. And if we look at what's going on here, this is actually just our code. And again, it looks a little silly, like there's these angle brackets, but we see we're just calling get async when we first enter this. And so the first time moveNext is called, it looks at this variable called num, and num is just whatever the current state is. And the current state, the first time this runs will always be -1. And since there is no case of -1, we jump into the default case, and that's where we call get async. Now, what the compiler does, or the code the compiler writes, will first look to see, did that task complete? Because sometimes we write methods that are async task, but we return task.completed. And it's pretty cool because the compiler is smart enough to know, hey, if that task is completed, we don't need to switch threads. We don't need to do that. It's expensive. We don't want to do it. And so the first thing it'll do will say, is that completed? Because if so, we can just move on. But we know in our example, we're calling an API. It's going to have to reach out. This is going to take a couple hundred milliseconds, if not a couple seconds. So it's not completed yet, which means we enter here where it updates the state to 0 and returns. And this return is how thread 1 is now free to return and interact with the user. But again, before it left, it set the state to 0. So as get async is now running on a background thread, once it finishes and it shouts back and says, hey, I'm all done, and thread 1 jumps back in, again, it sets this value of num to the current state, jumps into the switch, and now we're in state 0. So this is how thread 1 knows where to pick up where it left off. And in this case, it's a little strange because the compiler's using goto statements, and we probably don't and probably shouldn't use goto statements in our code. But all this is saying is to jump to this line, IL007E, which is down here. And in case 1, we can see our code again, where we're calling, first we're getting the result, setting that variable result to the get result value, and then ensuring we have a success status code. And then, again, just like last time, it kicks off read as stream async, and just like we expect, it first checks to see, is that already completed? If not, okay, I'm gonna go return, I'm thread 1, I'm gonna go hang out with the user so that our app doesn't freeze. And so this goes back and forth, and this is how the C# team was able to design for us async await. So like we get this pretty syntax here in our code where it just says we have this async keyword, we have this await keyword, it's very readable, we can read it top to bottom, left to right. But if you think about it, this didn't exist when C# was first created. So super, super smart people on the Microsoft runtime team were able to figure out a way to take an existing language, an existing runtime, and create this state machine for us. Well, us as the developers consuming it, we get to use this really cool syntax. So that's how it's working under the hood. But what I want to highlight for you is this try-catch block here. And if you look, this try-catch block consumes the entire code. So this try-catch block, again, I didn't write this. I don't have a try-catch block in my code. But this try-catch block takes all of the code from our async task method and puts it inside of a try-catch block, which means if any of my code throws an exception, it gets caught right here. It gets caught in this exception handler. And this is okay, because as long as you use the await keyword, this exception gets rethrown. But when I was first learning async and await,